Okay, so now we're going to talk about Delaunay complexes, and the basic motivation, if you will, for studying Delaunay complexes has to do with the fact that if you think about the complexes we've studied so far, nothing prevents you from having abstract simplices inside, which of much higher dimension potentially than the embedding dimension of the Euclidean space it's like you're in, right? So this clearly isn't really desirable if what you're trying to do with these sort of abstract complexes is to represent something which represents the underlying topology, if you will. It's like of it's like of points sampled from something again in some embedding space. So in any case, this is this idea of Delaunay complexes. Okay, so again, the problem with considering the nerves of a collection of points, a collection of sets. In RD is that they may lead to abstract simplicial complexes with simplices which have dimension which is larger than D, which is the dimension of the space you're embedding in, right? So we're going to try to set up the stage, if you will, for considering different types of complexes constructed from point cloud data, which will then allow you to have the property that they will have simplices which are most dimension D. Okay. So before we do this, it's like we're going to have to introduce the idea of sphere inversions. Okay. So so this involves anyway. So this approach, if you will, this will involve sort of Voronoi diagrams and Delaunay complexes. A finite set of points. Okay, and as a precursor to introducing all of this, we'll study sphere inversions. Okay, so we will first study sphere inversions. Okay, all right. So let me sort of talk about sphere inversions then. Okay, so inversions. So let SD denote the unit d-dimensional sphere centered at the origin in RD plus 1. Okay, so it's the unit D sphere centered at the origin in sort of D plus 1 dimensional space. Okay, and if you want to invert, it's like RD plus 1. So to invert RD plus 1, right, we map each point, which is not the origin, so each point of x, which is not the origin, okay, to a point along the same half line from the origin. Well, but whose distance, but whose distance from the origin is the reciprocal of the distance from x to the origin. Okay, all right. So let me sort of try to be a bit more precise about this. Okay, so what are you really doing, right? So let's say you have two-dimensional space, okay, and you have a point, say x here. All right, so what you want to do is you want to map x to another point, it's like which is along this half line which starts on the origin and goes through x, okay, with the property that let's call that x prime, which is the image of the sphere inversion map, with the property that the norm of x times the norm of x prime is equal to 1, right? So the distances are reciprocals of each other. Okay, so how do you do that? Well, you know if this is distance x, right, then this thing is distance 1 over the norm of x, right? And then you know what the unit vector is. The unit vector is x divided by the norm of x, and then you have to multiply it by a certain distance, which is 1 over the norm of x, right? So that's basically what you get, x divided by the norm of x squared. Okay, so more precisely, right, the inversion map let's just denote this by an I without a dot. Okay, I of x is equal to x over the norm of x squared. So this exchanges the insides and outsides of the sphere. So obviously it keeps the unit sphere fixed. Okay. Okay. So and it sort of takes something which is inside the sphere and maps it outside. Takes something the outside, maps it inside. So it exchanges the insides and outsides. While keeping the unit sphere invariant, right? Okay. So another observation, if you will, is what sphere inversion does to other spheres. Okay, so inversion maps spheres to spheres. But it doesn't necessarily map centers of spheres to centers of spheres. Okay, so let me then state the inversion lemma for you. So let's say that we have sigma, okay, be a d-sphere. It doesn't have to be the unit d-sphere centered at the origin. It can be centered anywhere. It can have whatever radius you want. Okay, let sigma be a d-sphere in Rd plus 1. All right, and then the observation is the following. If the origin is like not an element of sigma, if O is not an element of sigma, then the image it's like of that d-sphere under the sphere inversion, okay, induced by the unit sphere centered at the origin, right? This is going to be another d-sphere. And if the origin is an element of sigma, origin is an element of sigma, then the image of sigma under sphere inversion is a d-plane, so d-dimensional plane. Okay, so the bottom line is that if you take sphere inversion, okay, and one of the points you're trying to invert, right, is goes through the origin, if you will, of the sphere you're inverting with respect to, then it will map that d-sphere to a d-dimensional plane. So this sort of is maybe suggestive that you should think of d-planes really as something like d-spheres, but in some sort of non-degenerate sense. Okay, so this suggests that we should view the d-plane as a degenerate d-sphere. Okay, and of course you know that, I mean, just by limiting arguments, that if you look at where the origin gets mapped to, it gets mapped to the point at infinity. Okay, so this degenerate d-sphere, which sort of passes through the point at infinity. Okay, all right. So so again, it's like the basic idea is that if you have sphere inversions, it's like which keep this unit sphere fixed, right? You can, for example, and if you happen to have another sphere, okay, which goes through that origin, then the image of that under sphere inversion would be a plane, you know, and you can sort of think of that plane as eventually hitting the origin, if you will. Sorry, hitting infinity. Okay, all right. So let me just stop here for now.